Hello, welcome back. No handouts today. Homework number 3 is due on Thursday. No late days because we want to be able to hand out the solutions on Thursday in time for you to review for the midterm a week from today, 7 to 9 p.m. Truman Auditorium. Okay, let's see, where are we? We have been doing pipelining. At this stage, we have implemented a pipeline machine for the DLX processor. We discovered in the process that there were a bunch of data hazards that would stall the pipeline, and we handled them as best we could. We left one data hazard behind that we couldn't do anything about, for which we stalled. We then discovered that there were control hazards. There were hazards having to do with branches, and we did our best to eliminate them or to change the instruction set architecture, or we had to make the effect of those branches be as small as possible. So we're done. Our pipeline machine is finished. We can go home and finish the course. Well, not quite. For one thing, our marketing department has told us that this machine is not sellable unless we have floating point, because all the competitors have floating point. And floating point is a problem, because as soon as you add an instruction like floating point divide, which is guaranteed to take an awfully long time, and try to squeeze it into our narrow little execute cycle, we've got a problem. We've either got to widen the execute cycle, which is a waste for all the other instructions, or we've got to figure out some other way to handle the long operations. So that's one problem we have to address. The other problem we have to address is that the people who are running the operating system, all you computer science students out there, have told us that unless we figure out a way to do interrupts on this machine, it's not going to be terribly useful, or which is to say the operating system won't have enough to do if it doesn't have to handle interrupts. So we're going to have to figure out a way to make our machine handle interrupts, and that's a problem because we've got multiple instructions in execution at any one given time, and trying to keep the machine from making a mess of things as it takes this interrupt is going to be a challenge for us. So those are the two things we're going to handle today. Before I do that, I'd like to revisit just a couple of things from before and clear up some issues. Someone asked at the end of last class about the branch strategies we had taken, and I showed this chart that shows what the penalties were for each of the different strategies. And I wasn't clear which of these things we had done, which of these things we had not done, and what the final result is. Well, stall we clearly didn't do, and that was a bad thing to do. It was going to give us a 3-cycle penalty, so we decided we've got to find a better way. We decided that by moving the branch decision logic, both the target address computation and the decision making for whether conditional branches can branch, into the ID stage was a great thing to do. We could do it without much additional hardware. It cost us a single-cycle penalty in both cases. Well, there are a couple of other strategies we looked at for reducing the branch penalty even lower than a single cycle. One is to predict that the branch is going to be taken. Well, it turns out that on our DLX pipeline, although not necessarily on other pipelines, that's not a great thing to do. It doesn't give us any additional advantage because we can't start doing that any sooner than ID anyway. One thing we could do is say predict not taken, and in the case where the branch is in fact not taken, that would give us a 0-cycle penalty. We still have a 1-cycle penalty to cancel it and restart it if the branch is taken. So we could maybe have considered doing this and gotten down to, on the average, 1.09 effective cycles per instruction. But instead, we decided to basically change the instruction set architecture and allow us to execute the instruction following the branch, whether or not that branch is taken. Now, in a sense, you could say, and I guess the marketing department would say, that the penalty in that case is 0 for whether the branch is taken or not taken, because we're not doing any stalls. We executed an instruction, so the penalty is 0. Well, we're engineers and not marketeers, and we have to be more honest than that. And in fact, although we always execute an instruction, as we saw, some of those instructions are useless in the sense that we didn't need to do them for the computation. And if you, as we did before, go through that computation for how long the wastage is, it turns out to be about 0.07 of a cycle on the average. So to summarize, what we did is we moved the branch into the ID slot, and then we changed the instruction set architecture to allow a single delay slide after the branch, and that got us down to the final result. Any questions about that?
When you say that that's what we did, do you mean that's what we're going to be implementing on our assignment, or?
Well, that's the machine. This is a hypothetical machine, so we can do whatever we like to it. That's the final machine configuration that we decided on here. Yeah.
Well, it seemed like when you were talking about the branch delay and the dependency of the software, or creating the dependency between the instruction set and the hardware, that it wasn't such a good idea.
It wasn't such a good idea, but in fact it turns out to be the decision that most people are making. Most of the RISC processors have branch delay slots. I personally think that it might cross the line of mixture between implementation and architecture, but it's what people are doing.
Where does the 0.5 come from in both cases?
It comes from what we talked about before. It's basically looking statistically at how useful the branch delay slot is. And the slot is useful, which is to say it's an instruction you needed to execute about half of the time. That's not a precise number, it's a fuzzy number. Okay? Another question I got led me to believe there's a little bit of confusion in pipelining forwarding about distinctions between sort of logical forwarding and forwarding bypass paths. And I think what I'd like to do is go over a kind of systematic way of analyzing pipelining and looking for what forwarding paths we need and what implications that has in terms of stalls. And to do it for two different pipelines. Let's do it first for DLX where we know the answer, and then let's do it for another pipeline which is deeper, a pipeline more like the one that the NIPSAR 4000 uses, and see what answers we get to. So let's look at our traditional pipeline. I didn't prepare a slide for this, so I'll have to invent it as we go. Instruction fetch, instruction decode, execute, mem, write back. Let's write down a couple of instructions. After a while, this gets to be, oops, I got it wrong already. I guess the conclusion is I can't talk and write at the same time. It gets to be a mantra, IFID, execute, mem, and write back. Sort of like Om Mani Padme Hum. You guys don't remember that. That was from the 60s. And right back off the edge here. This is instruction I and I plus 1, I plus 2, I plus 3. Well, one of the things we need to do to look at forwarding in a systematic way is what are the sources of data and what are the destinations of data, and then look for all possible combinations. So for the DLX pipeline, the sources of data are the execute for an ALU operation, and the mem stage for a load operation. And where do the results go? Well, they go, again, to execute, to the input of execute for an ALU source operation, and to the input of mem for a store operation. So this is at the output of that stage, and this is at the input of that stage.
Mem is also a destination for branches.
There's some destination for?
Branches, isn't it?
Okay, what I'm looking for at the moment are not branch instructions, but just data forwarding. We're looking at the bypassing for data hazards. There are some interactions between the two when you look at instructions like jump register that requires the output of a register to, which may be forwarded from a previous instruction in order to compute the branch target address, but I don't want to deal with those right now. Okay, so let's look at all possible combinations of source and destination. We can go from execute to execute. We can go from execute to mem. We can go from mem to mem. And we can go from mem to execute. And those are the logical forwarding paths that we need. Now, the other question to ask is how many instructions forward, or to which instructions, do we need to do the forwarding? Well, let's say that we've got an ALU operation that is producing a result and a subsequent instruction needs to use that execute operation. Well, that's the case here. Let's say that instruction I produces the result. Certainly instruction I plus 1 needs to use the result forwarded to it, so there's a forwarding path here. Certainly instruction I plus 2 needs to use it because the write back doesn't occur until cycle, number the cycles here, 5, and instruction I plus 2 would need to have read its register operand in cycle 4. So there needs to be forwarding from execute of instruction I in cycle 3 to execute of instruction I plus 2 in cycle 5. Well, that's a logical forwarding path. I mean, you can put it in the diagram as a dotted line. That's the effect you want to get. But you can't do that directly because these things are happening at different times. You can only do forwarding from the end of one cycle to the beginning of the next cycle at the same time. So in fact, we've got to find another path to be able to get the output of that ALU to the input of this ALU 2 cycles later. And the way to do that is to use a forwarding path that comes from a different stage in the pipeline. So in fact, we can forward in the normal fashion the result of this ALU for that instruction into the mem stage. And then the forwarding path in the hardware goes from the mem stage of instruction I to the execute stage of instruction I plus 2. And that can happen at the same time, even though they're 2 instructions apart. Does that make sense? So there's a logical forwarding path, and there's a physical forwarding path. And what you have to wire into the machine are the physical forwarding paths. Yeah.
So your choice of physical path sort of depends on what hardware you have in the machine. And
that's right. Your choice of physical paths, in fact, depends. In this case, we don't have much choice. You could, I suppose, think about taking a physical path that forwarded from execute to the beginning of ID somehow. But you couldn't get it into the register file. You'd have to have an additional chain and another multiplexer to do that. But yes, there are options, and you have choices. And in fact, in the deeper pipeline, we'll see there are some obvious choices where we can make 2 different decisions based on what other hardware we happen to have around. Forwarding execute to execute can stop there because instruction I plus 3, if it needed an input in its execute phase, could have read the register directly out of the ID phase. Now again, this depends on this trick that we're assuming for our pipeline, that a register written in the write-back stage can be read by another instruction in its ID stage in the same cycle. That's a property of the register file that we've assumed. So the answer to how many instructions for execute to execute is I plus 1 and I plus 2, basically 2 instructions. And we found that we needed 2 physical paths to implement that. And these are the traditional ALU to ALU operations. One ALU operation that produces the result that the next ALU operation needs. Execute to memory instructions, well, those are ALU operations followed by a store operation. And we can go back and look at the same kinds of forwarding paths. We need to get it from execute in instruction I to mem in instruction I plus 1. And in fact, this is a case where we have 2 choices. We can do the forwarding of execute to execute and then propagate it down the pipeline in instruction I plus 1. Or we can do the forwarding in cycle 4 of mem to execute, assuming that the appropriate operand is continuing down the pipeline in instruction I, and forward to, forward to mem. You're right, forward to mem. Right. So we could do it by execute to execute, or we could invent a mem to mem forwarding path. In fact, we're going to need the mem to mem forwarding path later, so we still have that choice to do one or the other. And again, we need to forward it to I plus 1 and I plus 2. We don't need to forward to I plus 3. Notice that we need to forward to I plus 2 even though its mem cycle is past the write-back point for instruction I. Because even though mem is past that point, ID is not. And it doesn't read its operands in execute, it reads its operands back in ID. So, for execute to mem, we also need to forward to I+1 and I+2. Mem to mem are load instructions followed by store instructions. And in fact, this is the case where we're going to have to invent a new forwarding path, that mem to mem forwarding path. If I is a load and I+1 is a store, we're going to need the path of mem to mem. So we just added a new data path, a new set of multiplexers to cover that case. Right. For the case of I being a load and I+2 being a store, well, it looks like we almost have two choices. We could forward mem to execute and then forward it on to mem in I+2. Or we could try to forward right back to mem. The problem with that is that the path to forward from in the write back stage is not visible to us. It's buried inside the register file. And in fact, you'd have to have a 16 or 31 to 1 to multiple multiplexer in order to pick the right register in order to get that forwarding. So that wouldn't be a good choice. So in fact, the choice to use is to reuse the mem to execute path and forward it on to mem. And again, we have to forward to I+1, I+2, and not I+3. The last case is mem to execute. And that's the case of a load instruction followed by an ALU instruction that uses its result. So if we look at that, the result is available in mem. In order to be able to use it in I+1, we'd have to get it to the beginning of the execute cycle. So somehow we'd get it from the end of this mem cycle to the beginning of that execute cycle. No can do. Is there a question there?
I have a question.
Yeah.
Going back to the first execute, and you want to get down to I+2,
Right.
could you forward it down to the ID stage and where it's fetching the register and say, okay, well, you try and fetch the register I'm working on, and just forward it down that way?
You could. That's a question that he asked, but you'd have to add, in a different context, but you'd have to add additional logic. You couldn't do it inside the register file. You'd have to have a bypass path around the register file, and we can get away without it. Basically, we can use another path that we already need for something else, so why add the additional hardware? Okay, so we were doing the mem to execute path, and this is in fact the place where we discover that that's a hazard that we can't solve. There's no way, short of tachyons, to get the output of this mem stage to the input of this execute stage. So in fact, we discover our first hazard that requires a stall. A load followed by an ALU operation separated by one instruction works just fine, and we already have the forwarding path for it, mem to execute. Again, I+3 has no problem because the register has been written back and fetched in an ID. So in the case of mem to execute, we only have one instruction path to forward for, and that's I+2. So a total of, in some ways, 2, 4, 6, 7 different logical paths. In fact, we were able to implement it with 3 different feedback paths in the hardware, and those are the 3 paths that I showed on the original block diagram.
Question.
Yeah.
Say instruction I. Could you go back to the paper?
We go back to the paper.
Yeah. Say instruction I is
Instruction I.
it's an ALU instruction. Okay.
Okay, so this
And
is ALU.
instruction I+1 is a branch instruction.
Ah, you want to go back to branch instructions. Okay.
And if the branch decision depends on the result of the ALU instruction,
Yes.
must there be a store between
Yes.
these two instructions?
Yes. If the branch instruction depends on the result of the ALU instruction, you have to add additional stalls. Now, one of the reasons why we cleverly designed the DLX instruction set not to do that is not to have those stalls. In fact, DLX doesn't use the ALU in order to do branches in the ID stage. All it does is compare a register to 0 or not 0.
I think what he's asking is if the branch depends on the results of the previous ALU. If you said add into R1 and then you do a branch based on R1.
Right. If you do an add where the result is in R1 and then you do a branch based on R1. Yes, I guess you would need an additional cycle of delay there.
Well,
That depends on whether or not you're forwarding from the end of the cycle to the beginning of the forwarding from end to end or beginning to beginning of cycles. And
Okay, good point.
Last time you decided to forward from the end.
I
and
decided to
avoid the
forward
stall.
from end, right, because in fact that's the way the book does it. But you're right. If you move the forwarding path so that the forwarding goes into the end of the ID stage, then in fact you can get the output of the ALU back to the end of the ID in time to make that decision without taking an extra stall penalty.
So in the homework, can we say that we don't need a cycle?
That's right. You don't need the extra stall cycle in that case. Okay. Let's now look at another pipeline. Obviously, DLX is not the only kind of pipeline there is. The pipeline we're really going to look at and analyze is a so-called super pipeline, one that's used in the MIPS R4000. But I just wanted to point out that there are other pipelines as well. And if you wanted to design a register memory instruction pipeline, then you might need something which is a reorder or a change of the DLX pipeline. Instruction fetch and instruction decode occur in normal fashion, but in fact, to do the ALU operation, you might first need to do a data fetch. So the memory instruction for the memory cycle might occur before the execution. And in fact, if you wind up having to do an ALU operation in order to compute an effective address for the data fetch, you might wind up having another ALU operation here. So for register memory machines, it's not as obvious what the sequence of pipeline stages is, and it gets a bit more complicated. You may have multiple ALU stages. In some cases, you may have multiple memory stages as well. But the pipeline we want to look at in more detail is still a RISC-like 3-operand register machine. And I think I have another version of that slide on the first of the next handout. This is an H-stage pipeline. Basically, the idea is that it's the same kind of pipeline, except now memory operations are slower. So rather than an instruction fetch taking 1 cycle, an instruction fetch now takes 2 cycles. We do the standard kind of instruction decode and register fetch in the following cycle. And let's say that, in fact, we can do branch target address computation in the ID stage. The execute stage does ALU ops. It does effective address computation for data memory operations later. But let's assume that in this case, the branch condition determination is more complicated than in DLX. And it doesn't come out until the execute stage. Well, one of the effects of that is that we know the target before we know the condition. It gives us some more options in choosing branch strategies. This might be a case, for example, where an assumed taken approach, depending on the statistics, might work out, because we can get a 1-cycle leg up, so to speak, on fetching the target address compared to when the branch condition comes out. Now, we may have to nullify that 1 cycle in the case where the branch condition eventually tells us that we're not going to the target. But if we go to the target often enough, then the assumed taken in this pipeline may give us an advantage. Remember, for DLX, it gave us no advantage whatsoever. Following execute, we have 3 memory cycles. Fully pipelined, but it's a latency of 3 before we have written data or get the results back. And then followed by right back to the register file. Now, one of the reasons that you might want to do this so-called super pipelining, and there's nothing super about these kinds of pipelines. They're just deeper pipelines. But one of the effects is that you can often decrease the cycle time because you've allowed things that were sort of big to begin with, like memory fetches, to take multiple cycles. Because of that, let's assume that our register file can't be as clever as it was, that in fact, when you write a result to the register, it's not available in the same cycle to another instruction. In fact, you have to wait for the following cycle to get the register data out. So we're not getting any right back to ID forwarding for free. Well, let's take a look at the analysis of this pipeline and try to do the same kind of computation we did before.
Question?
Yeah.
Does the instruction fetch in memory actually, like, is it broken up into 2 or 3 pieces, or is it actually just accessing memory? It takes a lot longer.
It's actually broken up into 2 pieces in the sense that when one fetch is in the second piece, a different fetch can be in the first piece. So it's not just that it takes a lot longer, it's also fully pipelined.
So does that happen by having different ports, switching back and forth, or is there?
No, it may happen because there are multiple stages for the pipeline, that there might be a stage where you fetch something out of the cache, and then a stage where you're checking the tag to see whether the thing in the cache is actually the right data or not. That kind of thing. Searching for something here, which I may or may not be able to find. I thought I had prepared some extra blanks of this pipeline diagram, which we may need as I begin to doodle on it, but we'll see how we go. Okay, let's do the same kind of thing we did before. We have to decide what the sources are and what the destinations are for things in this pipeline. What other sources? Anybody? What stages? A little bit of audience participation here. Yeah.
From MEM3 and from EX are the stages where data can come from.
Right. So the output of the ALU in X produces results, and MEM3, the third stage of the multiple memory stage for a load instruction, produces results. What about the destinations? Where do we need results to go to? Somebody? EX. What else? MEM1. Right. For store instructions, we need to do that. So, in fact, let's write down all combinations. We need to go from execute to execute. We need to go from execute to MEM1. We need to go from MEM3 to execute. And we need to go from MEM3 to MEM1.
So in this machine, the branch target is also something that's only with immediates?
The branch target is, I'm sorry?
The branch target computation doesn't ever involve a register value, it's only immediate values, right?
Well, let's assume that for the time being. I want to concentrate on data forwarding and not complicate our lives with branches just yet. Okay, so this is an ALU to ALU operation, the execute to execute. What subsequent instructions do we need to go to? Well, the output of the execute is available here. We certainly need to forward to execute in I+1, execute in I+2, execute in I+3, execute in I+4. Execute in I+5, notice that although its ID phase is occurring at the same time the write-back is occurring for our original instruction, our assumption was that the register file wouldn't forward that for us, so in fact we have to wait one more cycle. So we have to forward as well to execute to I+5. So we're forwarding from I+1, I+2, I+3, I+4, and I+5. Now, one of the things we're going to watch out for in doing this analysis is a couple of things. One are the places where forwarding can't help us and we're going to have to stall, and there'll be more of them here than there were in the DLX pipeline. And the other is what the real physical forwarding paths are. The following slide asks some questions which we'll answer in the courses of this analysis, but I don't like the first question because I think the question about how many comparators are needed is basically an ambiguous one. We'll focus more on how many forwarding paths. We're going to need to be able to implement the forwarding. And the other thing we're going to watch out for is what instruction sequences cause stalls, and in particular what is the load delay. So let's go back to forwarding from execute to execute. Those are the logical forwarding paths from execute to to execute on each of the following instructions, what are the physical paths? Well, we can forward from execute to execute for one instruction away. For 2 instructions away, we'll need to forward from mem1 to execute. For 3 instructions away, from mem2 to execute. 4 instructions, mem3 to execute. And 5 instructions right back to execute. So if we keep track down on the bottom of the physical paths we need, we've got execute coming from execute, mem1, mem2, mem3, and right back. Okay, what about execute to mem1? That's an ALU operation followed by a store operation. Well, output of execute, we've got to get to the input of mem1 in the following cycle. Well, we could do it either by forwarding from execute to execute or by forwarding from mem1 to mem1. We've already got an execute to execute, so let's do that. We don't need any additional physical paths. We certainly have to forward to I+1. For execute to mem1 2 instructions later, we certainly need to do it. We already have a data path that will work for it, the mem1 to execute path, so we might as well use that. So we have to forward to I+2. And similarly down the line, the execute to mem1 has to go down as far as instruction I+5. And notice that in that case, we'd better do the forwarding from the end of write back to the beginning of execute, because there's nothing in the pipeline for instruction I past that point. There's nothing that we could feed, unless we invented another stage in the pipeline, there's nothing that we could use to feed the mem1 input of instruction I+5 unless we got it in a previous stage for that same instruction. So in fact, we forward, in worst case, up to 5 instructions later, and we can use the same forwarding logic, forwarding paths. Different logic, different decisions being made, but same data paths. With me so far? Okay, what about mem3 followed by an execute? Well, that's a load, the output of which is coming from mem3, followed by an ALU operation. Well, the output is coming from mem3. The input is going to execute of the following instruction. And again, this is one of these backward in time type things. No can do. Can't do it for instruction I+1. Can't do it for instruction I+2. Can't do it for instruction I+3. First instruction we can do it for is I+4. And we can also do it for I+5. Now notice this has given us the answer to one of our other questions, which is that we have stalls. See if I can write all of this on the same page. We have stalls for a load instruction followed by, let's say, an add instruction. And we have that stall if there are 0, 1, or 2 instructions in between the two. So this is I+1, I+2, I+3, and then finally at I+4, we can actually forward the results. So we've got one case of stalls identified. What about forwarding paths? We want to go from mem3 to execute in I+4. Well, in fact, we already have that path. We can go from mem3 to execute in I+4. We can go from write back in I to execute in I+5 and get the same effect. So we've got that path as well. Last case is mem3 followed by mem1, which is a load instruction followed by a store instruction. We want to go from the output of mem3 to the input of mem1. Well, can't do it for I+1, can't do it for I+2. We can do it for I+3, I+4, and I+5. +3, I+4, and I+5. And this identified another case of a stall. So if we have a load instruction followed by a store instruction separated by 0 or 1 instructions, then we have to stall some number of cycles. Obviously, if there's 1 instruction in between, we store one cycle. If there's no instructions in between, we stall 2 cycles. What about the forwarding paths? Well, we need to get from mem3 in instruction I to mem1 of instruction I plus 3. We don't have a path to do that. So in fact, this is a case where we're going to have to add an additional bypass path where mem1 gets the results of mem3. What about mem3 to mem1 of I plus 4? Well, we can do that with the mem3 to execute stage. And similarly for the I plus 5 forwarding, we can do that with the write back to execute forwarding path. So in fact, we wind up needing 1, 2, 3, 4, 5, 6 forwarding paths. I don't think you can do it with any less. You certainly can do it with more. You may, in order to do some of these forwarding paths, require some additional multiplexers and additional latch registers along the way. And this is only the beginning part of a detailed analysis that would say exactly what ALU, what multiplexers and what paths you need.
Question?
Yeah.
I think I know the answer to this, but I want clarification. If you have the execute to execute forwarding path,
Right.
could you get like from cycle 4 to cycle 6's execute by going execute to execute and then execute to execute again?
No, you can't, because you're using an instruction whose data paths are already busy for something else. If you're trying to forward from this instruction to this instruction, you can't use any of the stages of the instruction in between, because it's got other data in it. It's executing with different registers and different values, and you basically...
Well, right, but you're
allowed to
assuming
destroy
you
it.
got latches or whatever to forward this information already, aren't you?
Yeah. But you can't have additional latches that forward data that's not related to this instruction. You can only forward data which is related to the instruction being executed. And instruction I plus 1 is a totally unrelated instruction. Okay. Yeah.
So if you have an instruction in your instruction set that is that might compute an address and then store data, is it possible to have to use the same forwarding path twice when you're combining these physical ones? Once you need to maybe go down to the execute stage to compute the address, and the other you need to go down to the execute stage to put the contents of what you want to write.
Yes, I could see that you may, in a sufficiently complicated instruction set, you may need to do that.
So you might need two separate paths.
You may need two separate paths, or choose an alternate path rather than one of the paths. In a pipeline as complicated as this, you get to choose essentially make arbitrary choices about which of several paths separating two instructions you can use. And based on a more complicated instruction set where you might want to use it more than once, you might be able to make a different decision about which one to use, so you avoid the case where you use it more than once. Okay, I think we've answered most of the questions here. We understand how many forwarding paths. We talked about the instruction sequences that cause stalls. What about the branch delay? Let's just look at the simple case there. We made the decision that, well, our pipeline said that the branch condition was finally available at the end of execute. So if we're not doing anything clever, then at the end of execute, we know that the following instruction can be fetched, and that represents a 1, 2, 3 cycle delay away from the position that next instruction would normally have been fetched. So the sort of simple answer is that the branch delay is 3 cycles. Now, in fact, we can use some of those other techniques to try to speed that up. We can think about putting in branch delay slots. We can think about assume taken or assume not taken strategies and try to reduce the average branch delay. If we do sort of mindless thing and wait until both the target address and the condition code is ready, then the branch delay will be 3 cycles.
Could you repeat that again?
Starting from where?
The branch delay.
Okay. The definition of the pipeline said that the branch condition is available at the end of execute. The branch target was available at the end of ID. So if we pick the later of the two, then we know at the end of execute we could certainly begin to fetch the proper next instruction. So in cycle 5 in this example, we could do that. Normally, we would have fetched the next instruction beginning at cycle 2, so there's a 3-cycle penalty. Is that the part you wanted me to repeat? Okay. What about the load delay? How much is the load delay for this machine?
Three or 2 cycles, depending on the instruction that follows.
Exactly. It's 3 or 2. It's 3 in the case of a load followed by an ALU operation, and 2 in the case of a load followed by a store. Very good. Any questions? This is a kind of systematic way of analyzing pipelines that allow you to answer a lot of questions about forwarding and the stalls and delays and so forth.
Is R8 or R4000, is it a branch taken or branch not taken? How does the pipeline handle that?
It uses even more complicated things than that we haven't talked about, and we'll get to talk about probably in a week, having to do with branch predictions based on histories of each particular branch. It basically tries to keep track for each branch of what that branch did in the past, and based on that, it can predict for that branch whether to take it or not take it. So we'll see that later.
So the branch delay isn't always 3 cycles?
No. 3 cycles is sort of the worst case, and if you try to be clever about it, you can get it to be better than that, as we saw with the LX. And in fact, with the deeper pipelines, you have more opportunity to be clever, and especially if the branch condition and branch target are not available at the same time, that gives you more opportunities to move things around.
Can you go back to the your diagram again, under the stalls, and how many instructions you said we could insert in between?
Yes. Here.
Isn't it 1, 2, or 3 for that top one and 1 or 2 for the bottom?
Well, let's see. For load followed by an add, the load ALU case, we can make it work for instruction I plus 4. So if the load is instruction I, then this has to be instruction I plus 4 for it to work. Right? So we can. So this is I plus 1, this is I plus 2, this is I plus 3. These are the number of instructions you need to insert between the load and the add. Does that help any? Hello?
Well, so it's not 0 instructions, it's off, I mean it's...
Oh, if you put 0 instructions in, it's going to install. Right? I mean, that was the point. How many instructions can you put in there and still get it to install? Okay. Let's now start talking about interrupts and exceptions and look in particular. Yeah.
So then the load delay should actually be 1, 2, or 3 cycles, not just 2 or 3, depending on how many instructions you have between the load and the add or the load in the store.
Do I have a mistake here? Help me, Lance. Do I have this right?
Well, you could have a load and then some unrelated instruction between there, and then the store, and in that case, you'd have 1 load delay. Yeah, it's any number below 3.
Right. Yes, yes, that's right. It could be 1, 2, or 3 cycles. It's 3 cycles in the case where there are adjacent instructions. And if you start putting instructions in between, then the penalty you're charged is less because you've managed to fill those delay slots with something else.
Sorry?
Yeah.
In that case, couldn't it be even reduced to 0? I mean, if the next instruction is completely unrelated to the load?
If the next instruction after the load is unrelated, yes.
Couldn't be reduced to 0?
Yes. I mean,
yeah, so
certainly
it's
if you put
0
enough
and 2 or
instructions
3.
in between the load and the thing that needs it, then the delay is 0.
Yeah. So what do you mean by load delay? The worst case or...
The worst case.
So it's 3 or 2 or 3 only? I mean...
So it's 3 in the case of a load followed by an ALU operation, load followed by an ALU operation that needs the result of the load, right? And 2 in the case of a load followed by a store that needs the result of the load. Okay, interrupts and exceptions. Terminology is not consistent about this. I used to like terminology that said that interrupts were external events that caused instruction processing to stop, and that exceptions were internal events, things that were caused by the instruction itself, an exception or a fault. But that terminology is not particularly universal, so you just have to watch out what assumptions people are making about the difference between interrupts and exceptions and faults. But let's look in particular for DLX at what kind of interrupts or faults or exceptions can occur in each of the different stages. Well, in the instruction fetch, we're fetching from memory. Instructions are aligned on 32-bit boundaries. We could get a misaligned memory access if the program counter has an address which is not a multiple of 4. We could get a page fault if this is a virtual memory machine. We could get a memory protection violation if you don't have the appropriate access rights. And in fact, those are exactly the same kinds of errors or interrupts that could occur in memory stage, where it's loading or storing a data operand. Now, I'm considering an interrupt to be something that actually stops execution and causes it to begin execution in the operating system. I'm not including in this things like cache memory misses, which are handled, in most cases, entirely by the processor. It doesn't stop the execution of an instruction stream and start another one. It just may cause some hiccups, some stalls in the pipeline. In instruction decode, about the only thing that can happen that's bad is an illegal opcode, and that can cause an interrupt. In execution, various kinds of arithmetic problems, depending on the definition of the instruction set, could cause an interrupt, like an arithmetic overflow, if you've defined it that way in your instruction set architecture. And in write-back, nothing can happen. All combinations of all 5 write-back bits are possible. Even if you try to write back to register 0, it's not considered a fault. It just doesn't do it. So there's no interrupt or internally generated fault that can occur in write-back. Now, in other processors, and even for elaborations of DLX, there are lots of other kinds of things that can happen. There are many other arithmetic events, fixed and floating point underflows and overflows, divide by 0. For IEEE floating point operations, loss of significance is an interrupt that they require. Decimal numbers, not all values are valid, so that could cause coding errors. There are, if it's a machine with kernel and user state, lots of different privilege violations where processes in user state are trying to access kernel functions that are not available. There are the real I.O. interrupts, the asynchronous events that occur from outside the machine that cause you to want to stop execution. There may be debugging interrupts. Lots of machines have special hardware that allow you to cause traps when particular events occur, like writing to a specified area of memory or even fetching an instruction. And then there are machine checks. There are self-checking features within the machines that that may cause an interrupt to occur if something has been detected that represents a machine malfunction. Basically, what we need to have happen when this occurs, when any one of these interrupts or exceptions occur, is to stop executing the current instruction stream, change the program counter. We may also have to change the processor state if it's a kernel and user state machine, so that we enter a more privileged state. And in machines like the i86 and other CISCs, making that transition from a user state to a kernel state can be a very complex and expensive operation. But we're going to try the simple case first of a DLX-like machine that doesn't have those complications. But because of the pipelining, it has complications of its own. What we would like are precise interrupts. We want, if instruction I is the failing instruction, the one that is causing the interrupt, we want all instructions before I to essentially be complete, finished. No need to look at them again. And all instructions beginning with I to be unstarted, so to speak, to have nothing done for them, so that when we're completely done with processing the interrupt routine, we can restart at the failing instruction. Well, that turns out to be hard to do for a number of reasons. Remember that interrupts can occur anywhere during the execution of instruction, and we have multiple instructions in execution at once, and we'll see an example of how that causes a problem. Also, depending on your instruction set architecture, there may be instructions that partially update state information during their execution. Consider the auto-increment or auto-decrement modes, where if an instruction is partially executed, like some of these may be, restarting them is a problem because they've already done some damage, so to speak. Remember, this instruction is failing, but some of these are in the pipeline already and may have begun their execution. So the thing we would like to do is get precise interrupts. We'll see that that's hard, and we'll see some ways of making it work if we have to. But the alternative is to use imprecise interrupts, and in fact there have been machines that do that. That when the interrupt occurs, it basically leaves the machine in a state where you can't restart it. And sometimes that's okay. There are some places where you absolutely can't do that, and one are virtual memory page faults. Obviously, if you're going to fetch the page from disk, read it into memory, you're going to have to restart the instruction that caused the page fault. So that interrupt has to be precise. The IEEE standard for floating point operation requires, if you're going to be compliant with it, that floating point operations interrupts are precise. They have interrupts for things like imprecise results, which require that you can record some information or fix something about the operands and then resume execution, continue the operation of the instruction string. And it may be useful or important to allow invalid opcodes to be restartable. That's a technique that's used a lot to extend the instruction set of a machine. Let's say that you build a cheap version of your microprocessor that doesn't have floating point operations. You'd like the invalid floating point operations, invalid for your machine, to cause a trap in such a way that you can simulate the execution of that instruction and then restart with the instruction that follows it without them having been partially executed and causing any problems. Yeah?
So if you have an imprecise instruction and it gets an interrupt.
You mean an imprecise interrupt?
Yes, okay, sorry.
There shouldn't be any imprecise instructions.
Then you need to, you say it can't be restarted. Does that mean that that instruction then never gets executed? I mean,
well, not only that instruction never gets executed, but the rest of the instructions in your program don't get executed. And you get sort of a bad luck fault and a message from your computer saying your program is terminated.
So you don't have that in your list of things it won't work for. You don't have, let's say, an I/O interrupt. I mean, if every I/O interrupt threw all the instructions out of the pipeline.
Oh yes, okay. That you certainly need to add as an interrupt that has to be precise as an I/O operation. Those are sort of the easy cases because you get to decide where you want to take that interrupt exactly. Right? You can just stop feeding instructions into the pipeline, wait for the pipeline to be drained out, and then take the I/O interrupt. You've just taken a few cycles delay. So getting precise interrupts for I/O is not such a big deal. Getting precise interrupts for faults that are internally generated within the instruction while it's executed is a much bigger deal. Take a look at, even for the DLX pipeline, why we may have multiple interrupts and interrupts occurring out of order. Let's say that we have an add instruction that in fact causes an overflow. Well, that overflow is going to occur in the execute cycle of that instruction. Let's say it's followed by a load instruction whose address is not a multiple of 4 bytes and causes a memory alignment error. Well, that's going to occur in the mem cycle. You could argue that you could discover that earlier on, but let's say that the model is that you send that address to the memory and it comes back with a message saying unaligned. And then that's followed by a subtract instruction, which in fact doesn't even get past instruction fetch because there's a page fault, virtual memory page fault. So notice that here we've got 2 faults that are occurring at exactly the same time. And here we've got a fault that occurs earlier for a later instruction. This is an easier case because we can decide which order to take them in. This is a much harder case because if we take them in the order in which they occur, we're going to get a fault for a later instruction before the fault for an earlier instruction. So how do we fix these problems? Well, one at a time. Let's first handle the problem of how we do traps in general. Let's say that we only have one instruction which is faulting. We know that in DLX no state change occurs until mem or write back. So at the end of the mem stage or before write back, we can recognize a trap or an interrupt that's occurring and basically force a trap instruction into the pipeline. Trap instruction is basically like a jump. We force a jump into the pipeline that didn't appear in the instruction stream, and then turn off all of the writes, or turn all of the remaining instructions into no-ops, and then just let the trap instruction filter down into the pipeline and eventually execute and jump to the interrupt routine. So all of the instructions which are in partial stages of execution but haven't yet done anything are instantly turned into no-ops, and we can restart them later. One of the reasons that a trap instruction differs from a jump is that you've got to arrange somehow to give the faulting program counter to the trap routine. You can store it in a special register, you can push it on a stack, you've got to do something to give it to the trap routine. Now that program counter of the faulting instruction has been moving down the PC chain of our pipeline machine, and you can pick it off at the appropriate place to be able to store it in the special register or push it on the stack or do something like that. Now that's pretty easy. The problem is that saving one program counter may not be enough if we have a branch delay slot. Let's say that we have a conditional branch instruction. We have a following instruction which is going to be executed whether or not the branch instruction branches. And let's say that that add instruction causes an overflow. Well, which program counter are you going to save? You've got the program counter representing the address of the add instruction, which we clearly have to be able to redo. This is a model where we have precise interrupts. So if we save that program counter, and after the interrupt resume execution there, we're going to not take the branch. We're going to fall through. But what if the branch in fact was taken? Well, we might try to save that program counter, but then we won't be re-executing the add. So in fact, you wind up having to save multiple program counters. And in general, if there are n branch delay slots, you may have to save n plus 1 program counters in order to be able to correctly resume execution. Now, in fact, what some instructions like MIPS actually does is notice that because the branch is an instruction which doesn't have any side effects, you can re-execute it. So if a fault occurs on an instruction in the branch delay slot, then the PC that they save on the MIPS is the PC of the branch instruction. And after handling the interrupt, they go back and redo the branch instruction. One of the things you've got to be a little careful about there is to let the software know or give it enough information to discover exactly which instruction was faulting, because now it's pointing at the instruction before the one that actually caused the error. And if it's trying to do processing based on what the error is, it obviously needs to know what the appropriate thing is. An interesting question is, let's say that in this case you decided not to do that and you in fact saved two PCs. So we saved the PC of the delay slot and we saved the PC of the target. When we're ready to go back to return back from the interrupt routine, how do we get the PC delay instruction to be executed followed by the PC target instruction? Now, one thing we could do is sort of simulate this instruction. We could copy it somewhere, execute it in the user context, and then jump to the subtract instruction. But it turns out, and I won't go through it in detail, but you can muse about it later, that in fact you can use a branch delay slot jump in order to do that. If you return to a sequence of instructions that looks like jump to the PC delay slot, and in the delay slot of this jump, you put another jump instruction, which is a jump to the PC target. And in the delay slot of this jump instruction, you put a no-op. I think that this, in fact, has the effect of executing the instruction in the original branch delay slot, and then followed by a branch to the target in all subsequent instructions. Something to ponder over. I also further think that, in fact, this is generalizable, that if you have n branch delay slots, you can use this same trick to resume the appropriate instructions, the n branch delay instructions before getting to the eventual target. In any
How-
case, that's just a trick.
How's the branch decision saved?
How is the branch decision saved?
In other words, how do we know if we should execute the subtract or continue on from the add when we return from the interrupt?
If the branch executed, then you would save the address of this add instruction and the address of the subtract instruction. If the branch was not executed, then in fact in that case you can save only one PC, which is the address of the add instruction, or you could save the address of the add instruction and the address of the following instruction. So basically you know which way the branch went by which collection of PCs were saved. In the case where you're, like MIPS did, saving the address of the branch instruction, then there's no problem because you're going to re-execute the branch and remake that decision. Does that answer the question? Okay, that handles interrupts in general. Now let's consider what happens when we have multiple interrupts, either simultaneously or out of order. Well, in the case where two interrupts are occurring at the same time, that's an easy case. We simply take the interrupt for the earlier instruction. The later instruction presumably will be re-executed and rediscover the same fault and re-interrupt later. In fact, that may not occur if the fix-up for the original fault does something which causes the later instruction not to interrupt, then it won't interrupt. And in fact, that's the desired behavior. So that's just fine. Well, what happens in the harder case, where a fault for a later instruction occurs before one for an earlier instruction? Well, we can do two things. One is we can take the interrupts as they occur. Right? You can stop the previous instructions which have not completed. You can process the fault in the instruction that's faulting and then restart at the first instruction that didn't complete. A better solution, though, is to defer all interrupts down to the end of the pipeline. It makes a much simpler, certainly for the software, way of handling interrupts. Basically, we know that for the DLX pipeline, the commit point, the point at which all interrupt conditions are known, is at the end of mem. So we have mem, write back, execute, ID, and instruction fetch. At the end of mem, all the conditions that could possibly cause an interrupt, including the one at mem, are known. And we can decide that that's the point at which interrupts are to be recognized. So if an interrupt occurs in execute or occurs in ID, you basically stop the execution of that instruction, but continue to move down the pipeline a flag that says that this instruction is interrupting. When that instruction reaches the end of the mem cycle, then you recognize the interrupt. Basically what you're doing is forcing all of the interrupts to be recognized in the order in which the instructions were issued, regardless of where within the pipeline execution those interrupts occurred.
So, in other words, before you did I guess if you were doing a write, you would get the interrupt from the mem stage itself. But at any rate, you wouldn't allow an interrupted instruction to create any changes.
That's right. If the interrupt occurred in execute, or the interrupting condition arose during execute, and it was an instruction that used the mem cycle, you would not do the mem cycle. You would simply basically turn the instruction into a no-op, except that you would continue to forward the notation that this is an instruction which is causing an interrupt. And in fact, you did point out correctly that in the case of mem, the memory cycle has to recognize that it's an interrupting condition, has to not do the effect of the instruction, and raise the flag saying that this is an interrupting instruction. That's right. In the case of the DLX instruction, that's not a problem. But that's a good introduction to the next slide, actually, because in fact we solved the problem fairly neatly with DLX by forwarding an interrupt flag along. But for other instruction architectures, it can get a lot worse. Consider, for example, I mentioned this before, the state changes in the middle of an instruction, like an auto increment. How do you restart that instruction if it's partially executed? Well, one thing you can do is avoid changing the permanent state until later. But that's hard. It means a lot of temporary results have to be stored for the instruction. Consider a VAX-like instruction that increments the register 3 times. Remember that this second reference to the register has to use the already incremented result. So if you're not saving the incremented result back in the register file as you do this, you've got to save a temporary copy of it to be used in the remainder of this instruction. That turns out to be a hard thing to do. Rather than not making changes to the state, you can choose to change the state, but before you do so, save the original state of the instruction. So if an interrupt occurs, you can go back to restore the effect of that instruction, or undo the effect of that instruction by restoring, for example, the original register set. That's a possibility, and machines have done things like that. A third case is to let in fact the instruction be partially executed and provide some mechanism for the instruction to be resumed in the middle after the interrupt occurs. And you can do that by designing the instruction set to allow it, like the string instructions in the 8086, for example. They're very long executing instructions. They can take interrupts, either asynchronously or exceptions. But they store all of their state information in architecturally visible registers. So in fact, all you have to do to restart them in the middle is to branch back to them at the beginning. You start executing the instruction again, and it resumes where it left off because its state information is stored in the register set. If that special state information is not in the user-visible registers or user-visible state of the machine, you can in fact invent special state information that saves that information. So for the VAX, on some of the instructions, they, at interrupt time, save a flag as part of the processor status that says the first part of a particular instruction has already been done. And then either the software or the hardware could decide to use that first part done flag in order to resume the execution of that instruction. I don't know, in fact, for the VAX whether that first part done flag is something that the software uses to resume or something that the hardware uses automatically. Either one can work. Okay, so much for interrupts and the problems that they create. On to another topic, which we'll just have time to begin in this session, and that is multi-cycle operations, things like the floating point operations that our marketing department has demanded we add. People call these run-on instructions, instructions that take too long to accommodate in any reasonable fixed-length pipeline. Maybe even integer divide is like that, but certainly floating point operations, complex data types for strings and decimals and so forth, and a lot of the CISC addressing modes and other instructions. The problem is that the number of clock cycles for the execution part of an instruction will vary. It may, in fact, even vary at execution time based on the data. You can design some very efficient arithmetic units, multipliers and dividers, that, in fact, take a variable number of cycles depending on what the value of their operands are. Very hard to fit that into a fixed-size static pipeline. So instead of using a static pipeline, we have to now switch to a dynamic pipeline, a pipeline where not all instructions take the same amount of time through all the same stages. As long as we're at it, as long as we've bitten the bullet and are designing complications to handle that, we could even go back and redefine how some of the DLX instructions work. Remember that an ALU operation didn't have to go through the mem stage. A store instruction maybe didn't have to go back through the write-back stage, but because we had implemented our fixed 5-stage pipeline, we had no other choice. Well, now, as long as we're going to have the complication for these run-on instructions, we could go back and optimize some of the execution of the standard instructions as well. Let's look at a typical example of a pipeline that has to accommodate floating point operations. This is a pipeline that has the same instruction fetch, instruction decode, the same memory stage and write-back stage, except that the execute stage now is more complicated. It could be as simple as a single cycle as we had before. It could be, in this case, for the integer or floating point multiply, 2 separate stages, the first stage of which takes 3 cycles, the second stage of which takes 3 cycles, and these are fully pipelined. The result is that for the integer or floating point multiply, the latency, the time that it takes an instruction entering this execute phase to the time it gets out, is 6 cycles. But the repeat rate is 3 cycles, because an instruction stays in this first stage for 3 cycles before moving on to the next stage. So this is not a fully pipelined execution stage, it's a partially pipelined execution stage. For the integer operations, of course, the latency was 1 and the repeat rate was 1. It was just one cycle, one stage, and it's fully pipelined. It's in the null case. In the case of floating point add, it's a fully pipelined, at least as shown in this diagram, a fully pipelined execution unit. So, but there are 2 stages to it. So its latency is 2, but you can repeat a new entry into that floating point add pipeline every cycle. In the case of the floating point divide, in fact, it's a non-pipelined execution unit that takes 15 cycles. So the latency to produce a result is 15 cycles, and you can enter a new instruction into that cycle, into that stage only once every 15 cycles. We have now introduced a whole bunch of additional complications. We have structural hazards because some of these units are busy when you want to issue an additional cycle. We have more data hazards than we had before. We have write after write hazards because instructions are going to be exiting these execution units out of order. And next time we'll talk about how to solve those various problems.